Welcome to our final project of the Embedded Systems course at the University of South Florida. Our project is based on building a self-balancing car. A self-balancing car is a two-wheeled system controlled using a microcontroller that balances on its own, similar to balancing an inverted pendulum. In our project, we have created an advanced user interface via a web user interface that interacts the system through Wi-Fi. The web UI contains the required control buttons with a HTML backend that commands the car to move forward, reverse, left, right, and stop. More actions can be added if needed. The communication protocols used for this project are UART, I2C, Wi-Fi, and we have also built a custom communication protocol which we'll be explaining later. Now, let us look at the working of this project.
The information received from the web UI via Wi-Fi is received by the ESP8266 and is communicated to the PIC microcontroller via our custom-built communication protocol. The data received can be viewed on the onboard LEDs here. And this is the web UI. Every time we press a button, we can see the data received.
This car can balance even with a slight push given to it. After looking at the working of the self-balanced car, here we have a flowchart for the whole system, showing all the modules and protocols. Initially, the web UI is designed with the help of HTML backend, and it communicates command to our ESP8266 module via Wi-Fi. Then, the ESP8266 module is connected to PIC18F45K50 microcontroller through our custom-built communication protocol, which will be explained later in the video. The PIC controller communicates with the Arduino Mega via receiver transmitter protocol, that is USART. Further, Arduino Mega interfaces the motor via motor driver IC, and at the same time it interacts with the motion tracking or gyroscope device MPU6050 via I2C protocol, which detects the axis parameters for balancing the car. Now, let us take a brief look at the modules which are used in the self-balancing car.
This is the MPU6050 module, which has 3-axis accelerometer and 3-axis gyroscope integrated on a single chip. The accelerometer measures the force with respect to gravity. Thus, we calculate angle of the vehicle. The gyroscope can measure the angular velocity or the rate of change of angular position. These measures are taken along the X, Y, and Z axis. The TB6612FNG is a dual motor driver which is ideal for integrating two small DC motors to a microcontroller, and it can also be used to control a single bipolar stepper motor. It works based on the hedge bridge concept but are more efficient, and it allows more current to be delivered to the motors and less current drawn from the logic supply. The ESP8266 Wi-Fi module is a self-contained module which can host an application and can network from another application. It has a powerful onboard processing and has storage capacity which can be integrated with the sensors and other devices with minimal runtime. The Curiosity Development Board is the ideal form to use the strength of modern 8-bit PICs. We have mounted PIC18F45K50, which is an advanced 8-bit microcontroller that has a high performance core, flash program memory with self capability to read and write. It has an internal clock of 48 megahertz, which helps us get the real time feedback. It has 36 input output ports and supports I2C, SPI, UART, and USB 2.0 protocols. Last, we have taken a small help from Arduino Mega 2560 to perform complex math calculations using Kalman filter and 3D angle calculations to perform the balancing of the robot by supplying the required pulse width modulation output.
The design of the self-balancing robot is based on the inverted pendulum. Balancing an inverted pendulum is a challenge because it is inherently unstable. The balancing of our robot involves three stages: stop condition, moving condition, and the turning condition. The slightest disturbance from the equilibrium position results in a force away from the equilibrium position that further destabilizes the system. To measure the angle of tilt, we have the data from two sensors, accelerometer and gyroscope. The accelerometer measures the force with respect to the gravity. Thus, we can calculate the angle of a vehicle. But the problem with this is that there's a lot of error and noise. The gyroscope can measure the angular velocity, but the problem with this measurement is that the integration has a lot of deviation. In order to avoid such situations, we use Kalman filter. For further having an accurate result, we are integrating Kalman filter with PID controller. This uses tilt feedback to control the torque of the motors and keep the robot balanced. A PID controller continuously measures the tilt of the robot and calculates an error value, that is, the angle between the vertical and the deviation. The PID controller constantly tries to minimize this error by continuously adjusting the control variable, that is, the motor torque.
The custom-built protocol, as we mentioned earlier, is a simple 4-bit two-way communication protocol that uses a split-frame methodology by sending 4 bits at a time and 2 sets of them to send a complete byte. In this protocol, a byte can be successfully sent within 10 time instances, while it also has the capability of informing the master about a slave reboot or vice versa. So the system does not enter an ambiguous state. Moreover, it eliminates the dependency of a clock to synchronize between two devices running at different speeds. The working of this protocol starts with the higher nibble by placing them on the 4-bit data line and then turning on the transmit ready interrupt flag. Once the slave receives the nibble, it turns on an acknowledge flag that indicates the master to send the next nibble and turns off the TXIF flag, which is the transmit ready flag. The lower nibble is sent in the same way. We created the new custom protocol as we wanted to experience the complexity of communication design between two entirely different entities. Thank you so much for watching and stay tuned for our future projects.